professor. I'm allowed. My job. I get up here and say this every day. Some crazy guy rolled by our office hours the other day and sort of told one of the students that only 1% of people in the country would understand what you just said. Yep. So, of course, he also might be a college professor, so I shouldn't be too disparaging, but he seemed crazy. I don't know. All right, so we have crashing room. Okay, so I guess we got an exam tomorrow. I guess we should talk about stuff that's on the exam that you guys are interested in hearing me talk about. Those of you that did not haven't asked, I mean, I got a bunch of problems on the sheet. Anything that you'd like to see me talk about? Ideas you'd like to hear me talk about? 60 minutes, it's your time. Yep.
2B, just the B2Y part.
Okay. So how to compute it or what to do with it once you have it?
Both.
Okay. So this is problem 2B. And we have the function x is equal to t² plus 1, y is equal to t squared minus t. And the question says, figure out where the function determined by this path is concave up and concave down. Right? That's the basics of the question. So if we're talking about concavity, that means I'm going to have to compute a second derivative. To get the second derivative, I need the first derivative. That's easy to compute, so we'll just write that down real quick. In a parametric setting, dy dx equal to dy dt over dx dt, which is 2t minus 1 over 3t squared. Okay, now you have to remember how to get the formula for the second derivative. So the second derivative, d2y over dx squared, is the derivative with respect to t of dy dx divided by dx dt. So we took whatever we just computed, and we drop it right there. Right, so we take the t derivative of that, and then we divide by dx dt. Of course, I hate the quotient rule, so I'm not going to do it. I'm going to rewrite this as dy dx is equal to 2/3 of t to the minus 1 minus 1/3 of t to the minus 2. So I can take a derivative easily. I don't know. Quotient rule is just a recipe for disaster. Okay, so the t derivative of this, d by dt of dy dx, equal to minus 2/3 t to the minus 2 plus 2/3 t to the minus 3. Negative 2 comes down, hits that negative 1/3, turns into a positive 2. Stop me if I made a mistake somewhere, but that's that derivative. And so if I want the second derivative of the function, I need to take that and then divide it by dx dt. So d2y over dx squared is equal to this guy, e to the minus 2 plus 2/3 t to the minus 3 divided by dx dt, which I've already done, is 3t squared. And to finish the problem, so I can actually solve things, I'm gonna multiply the top and bottom of this by t cubed. I want the negative powers of t out of here. So take all of this and hit with a t cubed, and hit this with a t cubed, and counter that, and what you end up with is that this is equal to minus 2/3 t plus 2/3 divided by 3t to the fifth. Okay. So from this point, concavity is going to changes in concavity happen at critical points. So where does a critical point happen? When does this produce critical points? Numerator or denominator is equal to 0, right? Because critical points can happen when we have change of concavity can happen in situations like this, right? Where we flatten out in the horizontal direction, we change from concave down to concave up. Or they can happen where we have situations that look like this, right? So I mean, this is possible in parametric equations. You have this non-functional behavior where things actually get vertical, right? So the critical points here are going to happen when minus 2/3 t plus 2/3 is equal to 0, which happens at t equals 1. There's one critical point. Or where the denominator is equal to 0 and the thing is undefined, 3t to the 5th is equal to 0 happens if t is equal to 0. So there's your critical points. The two places that could be inflection points. Now we have to resort to pre-calculus. We're going to do a sine table real quick. So we have t is equal to 0. We have t is equal to 1. We are measuring the sine of the second derivative because that tells us concave up or concave down. So put in some test points. If you put -1 into this expression right here, you get a positive number divided by a negative number, which is negative. So we're using test points. If I tested t is equal to -1, that gives me a negative number. If I test 2, I get a negative number divided by a positive number, which is negative. So if I tested t equals 2, negative number. If you test 1/2, well, that's smaller than, I mean, that's like 1/3, right? But 1/2 in here, you get 2/3 minus 1/3, which is positive over positive. So it's positive in here. So the second derivative is telling you that this function changes from concave down to concave up at t equals 0 and from concave up to concave down at t equals 1. They're both inflection. All right. What else? Yep.
Remember 3D.
3D, which was find the tangent line to this graph when theta is equal to pi over 6. Okay, so I told you guys that I would give you on the front page of the exam, I'm going to give you this formula. This is the one formula you can just, I will give it to you. So polar derivatives. So if you have r is equal to f of theta, so a polar function, you can calculate the Cartesian derivative with dr d theta sine theta plus r cosine theta divided by dr d theta cosine theta minus r sine theta. It's not hard to derive this, but why are you going to spend your time doing that? Okay, so the particular function that we're dealing with here is 2 minus 3 cosine theta. So dr d theta is equal to 3 sine theta. I plug in 3 sine theta plus 2 minus 3 cosine theta and 3 sine theta cosine theta minus 2 minus 3 cosine theta sine theta. Now, I don't care if you algebraically simplify that. You just, if you got a problem like this, you just leave it. To get the actual slope, you have to plug in theta is equal to pi over 6. You can imagine that my impulse on an exam will be to give you something where some of these cancel out. I guess you can't really do that here because you put in like pi over 2, then you're going to get nothing to do. No, I think like pi over 2, for example, would have made this really nice. Pi over 6 makes it nastier. But anyway, you put in pi over 6, and you're going to end up with an expression. I'll just say m, the actual slope we're interested in, m, is equal to 3. Okay, now the sine of pi over 6 is root 3 over 2? No, 1/2 times 1/2. 2 minus 3 times root 3 over 2 and by 3 times 1/2 times root 3 over 2 minus 2 minus so boring.
Wait, what?
Did I do it wrong?
The last two.
What?
Like the
What did I?
that one and then the 1/2. That should be.
Oh, this is supposed to be,
I think.
that's a cosine up here, sorry. Okay. Is that better?
It should be plus on the top.
And a plus here. Yeah. Cool. All right. So we just got some slope. I promise you, I'm not gonna give you some number that's exhaustively, you have to write down 800,000 times on an exam, right? The idea here, so for my purposes, I'm gonna call this M. And I know the equation of the tangent line now is y minus y naught is equal to m times x minus x. I have m. I wrote down m equals this. I'm gonna use the symbol substitution here so I don't have to write it again. Where do x naught and y naught come from? Because this is a Cartesian equation. Where am I gonna get it? Where do I get an x naught and a y naught?
You have to convert, right?
You do. You have to plug in pi over 6 to this, and then convert from polar to Cartesian, and that's where that comes from. Exactly correct. The idea is if you take the original equation and you put in pi over 6, that's the theta. What's going to come out of this is the point 2 minus 3 root 3 over 2, comma pi over 6. This is in polar. And you just convert using x is equal to r cosine theta, and y is equal to r sine theta to get that. So you should write that out when you do it here. I will endeavor to make this easier to compute if I ask you this question on the exam. So the final answer is something like, I mean, it's this equation with x naught being equal to 2 minus the square root of it's 3 root 3 over 2 plus r cosine of theta is root 3 over 2 and y naught is 2 minus 3 root 3 over 2. Standard polar rectangular conversion. If you did get a problem like this where there's a ton of symbols or you made a mistake, you don't want to write this stuff over and over again, it's okay to tell me x naught is equal to this, y naught is equal to this, m is equal to this, and the tangent line is with those definitions of y minus y naught is equal to m minus x naught. If you define these quantities for me, you don't have to write them over again. What else? 4A. Find the area that lies inside the circle and outside the cardioid. Okay.
Is there a way to do this without having to draft it?
No. So if I do this on an exam, I'll give you I'm trying to separate plotting from the calculus. So I'll probably give you a picture of what it looks like. So you at least have the basic idea of what the region looks like. Okay. So on a review, I'm putting the ideas together because you're going to do both parts. On the exam, I'm trying to separate the ideas that are being tested. So 5 cosine theta looks like this. And this is 4A, right? And then the cardioid was, where is it? 2 minus 3 cosine theta? No, it's not right. 2 plus cosine theta. Okay. So 1, 2, 3. Not even cardioid, is it? It kind of lumps out on the other side. Whatever it is. Kind of comes through, does this sort of thing, the kidney bean shape. And the idea here is that we're looking for this area. Right? So we need to know that point, that one. And I'm going to remember when you're integrating these problems, you have to integrate this way. So that angle has to be smaller than this one. Even if you solve this trigonometrically and you end up with this angle being all the way around, you have to make sure that you start with a small angle and you end at the big one. So you're going around the circle in the right direction. Okay, so how do you find the points of intersection? Set them equal. That's an old school way to think about this. Hopefully, your professor has set up a problem where it's relatively easy to do. So we do 5 cosine theta is equal to 2 plus cosine theta. So that means that 4 cosine theta is equal to 2. So cosine theta is 1/2. You're going to be careful here because if you look at that equation and you think of the unit circle, or your hastily sketched unit circle you did in the first minute of the exam, you're going to write down theta is equal to pi over 3 and 5 pi over 3. The problem is if you use these values for your limits of integration, you're going to be integrating this way because you're going from pi over 3 to 5 pi over 3, which means you're rotating around the circle in the positive direction, which will give you the wrong area. Okay. So is there a co-terminal angle to 5 pi over 3 that starts before pi over 3? Yeah, I'd use negative pi over 3 instead, right? You should think of this as being minus pi over 3 when you integrate up to pi over 3, because that starts at a low number and integrates to a bigger one. So you're going in the right direction around the circle. So this problem is the integral of 1/2 minus pi over 3 pi over 3 of outside radius squared minus inside radius squared theta. Right? Outside, I mean, you could break this into 2 integrals, or you can think about it this way, it doesn't matter. What I care that you know here is that area is 1/2 r squared d theta. The picture will actually help you identify which is which. In this case, the outside radius is going to be given by 5 cosine of theta. The inside radius, little r, is going to be equal to 2 plus cosine theta. Five cosine squared theta minus 2 plus cosine theta squared d theta. 2 things where people go wrong on a question like this: they forget to multiply this out. They just throw it away because, like, who the hell wants to FOIL the middle integral? And the other thing is you neglect to use the conversion for cosine squared or sine squared. From minus pi over 3 pi over 3. I think after you've done multiplying all this out, you end up with that's a negative cosine. It's like 24 cosine squared theta minus 4 cosine theta. When you're done with all the algebra, this is what's left over. You FOIL this, which gets you 4 minus 4 cosine theta minus cosine squared theta. Minus cosine squared hits the 25 cosine squared, turns into 24 cosine squared. Only one hard step left in this problem, which is that's easy to integrate. That's easy to integrate. Only one way to integrate that one, which is to write cosine squared theta is 1/2 minus 1/2 cosine of 2. Okay. Yep.
What was the sine version of that?
The sine version. There is a, yeah, so the sine squared, sorry, this is plus, sorry. The sine squared theta version is the opposite sign. So it's plus for cosine and minus for sine. This is the sort of thing, again, I mean, since I'm telling you to memorize it, what that really means is, can you memorize it long enough to write it down on the front page of your exam after I hand it out, right? So if you're having trouble holding these in your head, get them written down early before your mind is blown out by a math test. Yep.
When we do those, I remember like if theta stays like 2 theta, how do we like manipulate it when we're like?
Right. So the general rule here is, I mean, so I guess the first thing we should say is this problem with all of its pieces is probably too long for the exam because there's a lot of moving parts here. I could ask you the area inside of just one piece of it, and you're going to be faced with the same issue, right? Which is that there's a cosine squared in here. But I could give you something that moves faster, in which case, what you should think is the general formula here is that the cosine squared of anything is equal to 1/2 plus 1/2 times the cosine of 2 times the anything. So that rule holds for anything you substitute into it. So for example, if you ran into a cosine squared of 6 theta, you still can't integrate this because it's a cosine squared, but you can still apply this formula to get the square out as long as you double whatever was inside. 6 theta turns into 12 theta, which is why this is called the double angle formula. What else?
Did you do 12.1B?
12.1b. Sketch or describe in words the region of R3 defined by these equations. Okay, this is an excellent exercise. Okay, so the point of this is to get you thinking about the fact that these equations mean different things in different variable setups. So if you're in R2, this is a collection of points x and y, you have no free choices. In regular old R2, this is a circle, because the relationship of x and y is completely determined by this equation, right? In R3, now let's say you're in R3, there's no z in that equation, which means z is a free choice. This holds for all z's, right? So that means any choice of z that you make, that circle is in the set. But if I have a circle, but I can move the z values anywhere, I don't have a circle, I have a cylinder, where the cross sections of the cylinder satisfy this equation, but z was free. No constraint on the choice of z. Now I take that and I intersect it. So the answer is this thing in R3 is a cylinder because there's this extra variable running around. Now I take that and I cut through it with this guy. What sort of shape is that? Well, it's every point that has the form x, y, minus 1. If I have a fixed height, but I can slide anywhere I want in x and y, what am I looking at? Not a circle. X, just this all by itself. Forget this for a second, right? Just this shape, because in two variables, this would just be a line, right? If I say one variable is fixed, but the other one could be anything, it's a line. Yep. It's a plane, right? It's a plane where any x and y you choose, as long as z is minus 1, is in this set. So what we're doing is we're saying, okay, take this cylinder, and then around it, put this plane. And how are these things going to intersect each other? Well, you can imagine that there's going to be this cut mark on the side of the cylinder where the plane cuts through it. So the cylinder is given by this equation and the plane is given by this one, but where they agree with each other is actually just on this circle right here. So this circle, that's the intersection. Yep. It is a cross section, yeah. It's the cross section of the cylinder located at z equals minus 1. You can say that if you like. Yep. All right, what else? Sorry about the waiting room there. It doesn't happen if you log in with your Cal Poly account, I think. But my bad. It's still recorded the first part. All right, what else? Yep. 10.3b. Identify the curve by finding our Cartesian equation. Okay. So the general strategy that you should take when you're going from polar to Cartesian or Cartesian to polar is to have the substitutions down. So these substitutions are really useful when you're going from a Cartesian equation to a polar one, because you can just replace x and y and then solve for r. You don't even need to if you weasel out by saying implicitly defines a function in terms of theta, right? If you're going the other way, so in this case we have a polar equation. So this is usually used when you're going from polar, or sorry, from Cartesian to polar. The other way is a little trickier. So you have this setup. Normally when we're going from polar to Cartesian, the most straightforward way to get started is to use these three substitutions. Since x is equal to r cosine theta, everywhere I see a cosine theta, I can put in x over r. Everywhere I see a sine theta, I could put a y over r. And if I happen to see an r squared, I could replace it with an x squared plus y squared. And what you do is you put all that stuff in and then hope everything cancels and there's no r's left over. So that's the approach we're going to take here. We're going to jam these substitutions in here, and hopefully the r is canceled. There's not even an r squared, so I'm not going to use this one in this case. So now there's a lot of different approaches to this. I'm going to point out that the fastest one would be to multiply both sides of this by cosine and get r cosine theta is equal to 4, but r cosine theta is x. That's the fastest way to do the problem. Okay. If you didn't see that, because you didn't manipulate, you're not comfortable with these sort of manipulations, what you could do instead is say, okay, well, here's a second way to do it. If cosine theta is x over r, then secant theta must be r over x. So another approach would be to say, oh, well, this is r is equal to 4 times r over x. If you multiply both sides by x, you get xr is equal to 4r, and cancel the r's out, and you get x equals 4. There's a second way to do it. A third way to do it would be to say, well, I've got 4 and then a 1 over a cosine of theta, because I know that secant is 1 over cosine. I know that cosine is equal to x over r, and that gets me the 4r over x I had last time. This also ends up algebraically resulting in the equation x is equal to 4. So a lot of different approaches that work here, right? But the key idea is put these in, and then mightily hope that the r is all here. Yep.
You probably should just multiply cosine theta, like the 1 over, multiply cosine theta to the other side.
Uh-huh. I think that's the first line.
Okay.
Yeah.
How do you find y?
There is no y. What sort of equation is that? This is weird as this seems. This is the equation of the vertical line that goes through x is equal to 4. If you plotted this in polar coordinates, you're going to get something that looks like this. Right? So secants in polar coordinates turn into vertical lines. Cosecants turn into horizontal lines. That should give you a warning that cosecants and secants are not terribly, or the lines kind of suck in polar coordinates, right? If you use polar coordinates when things are circular for a reason. What else?
Do 9c.
9c. Find which, okay, this is a good one. 9c. So this is the intersection points. Point of a line. And a plane. This one seems harder than it actually is. So r of t equal to 2, 0, 5 times 3 minus 4, 1. And we're intersecting the plane. 4x plus 5y minus 2z equal to 18. So if two things are going to intersect each other, then they have to be equal in some sense, right? And that's what happens where things intersect, is they have to be equal. The problem is I don't have anything to be equal here. There's no equality, because I have this is a vector form and this is not. So what I'm going to do is I'm going to rewrite the line in parametric form. So if I rewrite this in parametric form, I get x is equal to 2 plus 3t, y is equal to 0 plus negative 4t, z is 5 plus 1t. So now I've got equalities, right? X, y, and z on the one hand have to be equal to this, but they also have to satisfy this equality. So I just plug these into that and solve for t. 4 times 2 plus 3t, 5 times minus 4t, plus minus 2 times 5 plus t is equal to 18. So what do you get? 8, 12t, minus 20t, and minus 10, and minus 2t is equal to 18. I think when you're done solving this, it comes out to 2. Yeah. I mean, subtract the 28 minus 8. Yeah, t is, I think this minus 2. After you're doing the algebra. You solve this for t, you get t is minus 2. Are you done? Well, no, because I didn't ask you the time value where the intersection happened. I asked you for the point where they intersect. So make sure you answer the question that was asked. So you do this, I mean, this is just algebra. When you do the algebra, you get t is minus 2. The point is what we're interested in, not the parameter value where it happened. So I've got to take that 2 and or negative 2 and plug it into these equations to get x equal to -4, y is equal to 8, z is equal to minus 3. I missed something? 3? Oh yeah, 5 minus 2, 3. So that is the point of intersection. The only tricky part about this question is realizing you have to change the vector line into the parametric equation and then plug it in to the plane. And I promise there'll be a quarter of the class that forgets after they find the t to go back and plug it in and get the point that was asked for. So that's a detail to pay attention to. Yep.
When we're graphing polar curves, like especially for the pedals, like how many points do you want?
I'm not going to give you a pedal problem to graph.
Oh, okay.
Right. The pedal graphs take so long to do. You're going to get you are going to get a graph, a polar graph in the cardioid family, right? The sort of a plus b sine theta or a plus b cosine theta. I don't think it's reasonable for me to ask you guys to, I mean, I would do it on the homework, and if you had more time, I'd ask you to do that. Like maybe on the final, I'd ask you to do a simple pedal problem. But the general answer there is enough points to understand what's happening. And then use symmetry.
Yeah.
Right. So typically on a problem like that, like 6 points, somewhere between 4 and 6 points is enough to get an idea of what's happening on a board graph. Okay. So yeah, I will not ask you a pedal problem on this test. Even though they're my favorite. They're so pretty. So actually, since we're here, if you asked that question, let's talk a little bit about how I would approach graphing something in the cardioid family. So you should start one of these problems with a general idea of what it is that you're plotting. So if you get something in the R of theta is equal to a plus b cosine, well, let's just write one down. R is equal to 3 plus 2 cosine theta. Say. I'm actually going to write down what I think this thing looks like, the general outline of this shape, by just plotting what happens in the 4 cardinal directions. So 0, pi over 2, pi, and 3 pi over 2. And then I'm going to fill in anything that I'm missing with a couple of extra points if I'm not clear about what's happening. So when you put 0 in here, well, cosine of 0 is 1. So I get 3 plus 2. Pi over 2 turns cosine into nothing. This is 3. Pi turns cosine into -1. And 3 pi over 2 turns cosine into nothing, which gets me 3. So right out the gate, I'm going to write down, okay, in the 0 direction, I had radius 5. In the pi over 2 direction, I had radius 3. In the pi direction, I have radius 1. And in the 3 pi over 2 direction, I have radius 3. Right there, I've got a good idea of what's going on with this, especially if I know that functions in the family can only have 3 shapes. There's 3 sorts of things that can, I mean, really there's 4, but there's 3. Basically, I can have the actual cardioid shape. That happens when those numbers are equal to each other. Or I can have the shape where I got the sort of kidney bean looking thing. That happens when, say, this would be an example of that, like the one I just drew, right? When this number is smaller than that one. I sort of get a defective cardioid because I don't get close enough in to make a point. The other possibility is that this number is larger than that one. So if I had 2 plus 3 cosine theta, that falls into the family that does this. So the relative sizes of these tell you which family you happen to be in. And that's why it's enough to know what's going on in this question just by looking at these 4 directions. Now, if I was going to put 2 more points in here to make this graph more accurate, I might try to figure out what's happening in this direction and in this one, so I can accurately locate the back half of the kidney bean. Okay. So I'm going to choose my next points based on that computation, on that observation. I would like to know what happens in this direction and in that one. So I'm going to feed in 2 pi over 3. And then I'm going to use symmetry, because if I put in 2 pi over 3, I know whatever the radius is down here has to be the same. So what happens at 2 pi over 3? 3 plus 2 times the cosine of 2 pi over 3 is pi over 3. It's negative 1/2. Yeah. This gets me 2. So 2 pi over 3, I go 2 units out. And that means I also go 2 units out in the 4 pi over 3 direction as well. So this I would consider to be enough information to sketch this graph. All right, so it's an egg. Ish. I'm not asking for like, minute precision over here. But try to make your points as these plots are difficult. Yeah. If it's a cosine, the answer to that is yes. So, and the reason that that's true is because like cosine values, I mean, this function, the cosine of the cosine is positive over here and negative over here. And that's why you get this x-axis symmetry. The sines will be, if this sort of family with the sine will always be symmetric this way instead. What else? Two C. Find the area enclosed by this. Okay, so this question is a little bit harder than I intended it to be. The basic idea here is I didn't make the observation, or I left out the limits of integration. You can derive the limits of integration for this question from the fact that I tell you that x is equal to t squared minus 2t, which means this has intercepts, and x will be equal to 0, which means this has y intercepts. When x is equal to 0, which happens when t times t minus 2 is equal to 0. So t is 0, t is 2. These are the intercepts that we're going to be working with. Okay, so that's I did not mean to write a question down where I can get limits of integration. It's supposed to be more basic than that. We'll use these for the limits. Now, why did I choose y-intercepts? Because I'm supposed to be finding the area relative to the y-axis in this question, right? And that means whatever the function is doing, it doesn't actually matter. I'm going to draw something. It does not matter if it's the actual graph. Let's just say it looks like that. Okay. We're going to use this picture to try to figure out what formula we should be using, or we can memorize the formula. But if I was finding area this way, is this y as a function of x or x as a function of y? If I was doing this type of integral. X is a function of y here, because we're working relative. It's going to be a dy integral. So this would be x is f of y type setup. And if you wrote an integral of this area down, it would look like the integral from a to b of x dy. This is a method for keeping straight which formula works in the problem. That's why I'm doing it the long way. Now, I know that x is equal to this. The dy, this is not going to be a dy integral. It's going to be a dt integral. How can I get the dt in there? Well, I make the observation that dy is dy dt, and I can compute that derivative, right? So I think the book would have written this out as the integral of f g prime dt. But I think it's actually easier to keep track of what's going on if you have a picture in your head of this one of these dy integrals. You're just transforming the dy into a dt with this observation. And so the integral you do here is the integral from 0 to 2 of the x function times the derivative of the y function. I can write the y function down. Root g, right? The other approach to this question, if you want to do it from a formula perspective instead of like sort of an intuitive picture perspective, is to remember there's just two formulas. If you're working around the y-axis, the area with respect to the y-axis is the integral from a to b of f of t g prime of t dt. This is the book's notation for this. And if you're working around the x-axis, then it's g of t prime of t dt. So the intuition there is just to try to help you keep track of which one you use. Yep.
Can you just eliminate the parameter?
Yeah, you can actually, yes. Once you've identified the, now remember, if you do that though, don't use these as the limits of integration. You get points that correspond to those. But yeah, absolutely. You can limit the parameter. Yep. Yeah, not always an option that's available, but yes. What f and g happen to be? Oh, because the problem tells you with respect to which axis, right? So this problem says find the area enclosed by this and the y-axis, which means you're looking for an area that's trapped against the y-axis, which means you're using this formula. What else? Eight E? The area of the parallelogram problem?
Yeah.
All right. Okay, so the only thing you have to remember, the whole point of this is just to remember that if you have a vector A and you have a vector B and they make some parallelogram, that the area of this is the length of the cross product of A and B. Right, so the magnitude of the cross product tells you the area of the parallelogram. So of course, I can't use the length of the cross product unless I actually have the cross product. So the question says, find the area of the parallelogram determined by the vectors 1, 1, 1, and minus 1, 2, 3. So we'll compute the cross product. You want to see this written out, or can I just write down what it is?
Just write it down.
All right. All right, so you get 3 minus with I, and then that's 3 plus 1, which is 4, so minus 4j, and 2 minus 3k. I strongly discourage you from doing what I just did on the exam, right? Because if you make a mistake and there's no work, I can't give you any credit, right? So yes, you can eyeball these cross products a lot of times. Just be careful because you're playing with fire if you do that. If I make a mistake on the board, you guys yell at me and I stop. Okay, so A cross B equal to 1 minus 4, 3. We can check real quick to see to make sure that they're actually orthogonal real quick, right? So if I take 1 minus 4, 3, and I dot it with the vector 1, 1, 1, I get 1 minus 4 plus 3, which is 0. Okay, cool, I believe my. Okay, so what I used here is the fact that the vector that I got dotted with 1, 1, 1 is 0, which means they're perpendicular, which is a check on my own work, right? You should do that if you have time, if you compute a cross product. Make sure that you got the right one. So what it says is the area is equal to the magnitude of that vector. The magnitude of a vector is just the square of each of the components out of that. Which is 1 plus 9 plus 16, which is 26. And I'm actually gonna do the next one too, which is the scalar triple product problem real quick. So the scalar triple product question, which is 9C, true or false question that says, if A, B, and C lie in the same plane, then A dotted with B cross C is 0. So you don't actually need to know anything about volumes to do this. If A, B, and C are in the same plane, what direction does B cross C point? I've got B and C right here, and I compute their cross product. What relationship does B cross C have to the plane that they're all sitting inside? It's orthogonal, right? B cross C. Here, I'm going to make my. Wait, hold on. Wait, right hand. Shit. Okay, so I'll put B here and C here, so I satisfy the right hand there. Now B cross C points this way. Right? If A, B, and C are in the same plane, and I take their cross product, the vector that results points out and is perpendicular to every other vector in this plane. So where's A? In the plane, right? So what's the relationship of A and this cross product? So what's their dot product? So the answer is true, because B cross C is perpendicular to everything else in the plane, but A is in the plane, so it's perpendicular to this. This is true. Or the fancy volume answer is A, B, and C don't measure a parallel pipette at all. It's flat, it has no volume, but the scalar triple product is a measure of volume. So the volume of the parallel pipette they form is nothing, because it's flat. That's the slick way to do it. In either case, like the idea here is that you can work your way through the notion that this is orthogonal to everything in the plane they determine, but A happens to be in the same plane, and so therefore its dot must be 0. So this is not a hard question, but it's involved because it chains like 3 ideas together. Okay, any last minute desperation questions before I let you go? I will be on Slack. I promise I will extend all of the deadlines for the homework that was due this week to next week. I just haven't done that yet. They'll all be due next week. And yeah, I'll see you guys. Oh wait, yep. What I post. It's already up. I apologize in advance though that some of the first questions are disordered because I got confused and did some of the answers to 3 before I finished 2. So yep. Quiz 6, I'd be happy to do that. Especially if you send me a reminder so that when I get back to my office, I remember to do it. All right, good luck, guys. See you tomorrow.
I know the rules for what